and welcome to the April meeting of the PAS. We're fortunate to have an excellent speaker lined up tonight. And as you heard Rick stating, giving you a kind of an update for what's coming up next month, we might have him as a speaker, we might be able to find someone else. So it's definitely a fluid situation. So we'll keep everybody posted on that. Just keep checking back to the website. As you all know, I mean, we're still in the midst of shutdowns and whatnot. Foothill College is still closed, so there's no access to the telescope yet at this time. Although the club's Oak Ridge site is accessible for folks who have access to that site.
How we do this?
And no other updates to report, so I would like to introduce our speaker. So Dr. Pascal Lee is who's going to be speaking with us tonight. He's a planetary scientist at the Mars Institute, the SETI Institute, and the NASA Ames Research Center in Mountain View. He studied physics and geology at the University of Paris and got his PhD in astronomy and space sciences at Cornell, where he was Carl Sagan's last TA, which is pretty cool. In support of his Mars and moon research, Dr. Lee has led over 30 expeditions to the Arctic and Antarctica, and including wintering over in Antarctica in 1988. And I'm just curious, Pascal, which station was that, at the South Pole?
No, that was at the French base, Dumont d'Urville Station, which
okay.
In the summer's on the coast, but in the winter is locked in, far into the sea ice.
Okay. That's a whole other talk right there. He has written a children's science book titled Mission Mars and has starred in an award-winning 2016 documentary film titled Passage to Mars. So anyway, with all this wonderful activity, he could easily give us 10 talks. So, but tonight he's definitely got something lined up really nice. And Pascal, over to you.
Thank you. Well, first of all, thank you everybody at the Peninsula Astronomical Society. I really appreciate your having me. And I owe special thanks to Brian Day for roping me into this. So tonight I'd like to talk to you about something that's really dear to my heart, which is the work that we've been doing up on Devon Island in the high Arctic for the past quarter century. In fact, I moved to California about 25 years ago, once I left grad school, and I have yet to spend a summer at the beach in California. Every summer, my teammates and I head up to Devon Island, which is this godforsaken island in the Arctic, and we are very happy there. This is Mars on Earth. We think we're learning lessons about Mars science, about Mars exploration, but as a result, I have yet to go surf and try my luck at that. This past year, we could not go for the first time in 24 years. But because of COVID, I couldn't go to the beach either. So there you have it. So tonight we're going to talk about Devon Island, and I wanted to give you a version of the talk where I spent a little bit of time telling you about the history of the island, about how it connects to humanity's quest to explore in general, and also why in the first place we want to go to Mars, since that's what we're trying to plan up on Devon Island. And before I jump forward, I need to throw out a disclaimer. The opinions expressed here are just my own. NASA is a sponsor of my research, a part of it, but is not responsible for whatever I'm going to be saying here. And then the SETI Institute, which is also one of my home institutions, probably wants plausible deniability as well. So this is just my talk. Okay. Okay, how do I move forward? I don't seem to be able to move forward. Oh, there you go. Thank you. So this is where we want to go, down the road at least, planet Mars. And we are interested in Mars, of course, and you're an astronomical society, so I won't insult you with a lot of basic information, but still, for those who might not realize this, Mars is not the closest planet to us. It's actually Venus. Venus is actually closer to the Earth in size, but of course, Venus is closer to the sun. It has a environmental conditions at the surface that are really deadly, essentially, but in a way that is quite irreversible, in the sense that it's hard to do anything about, with humans at the surface of Venus. Temperatures at the surface of Venus are around 495 degrees Celsius. That's the temperature inside a pizza oven while you are baking pizza. The atmospheric pressure is 90 bars. So that's what you have in the ocean at a depth of about 900 meters. It rains sulfuric acid. I mean, it's a hellish place, literally. Mars, on the other hand, is a lot more friendly in that regard. It's colder, of course, than the Earth. It's farther out from the sun, and it has also 2 little moons, which are going to be of interest to us down the road. But Mars is more manageable as a destination, and that's why we've been very much focused on trying to get humans to Mars. And of course, there's the factor that Mars might shed some light on the origins of life on Earth, and Mars itself might have experienced an origin of life as well. So we'll talk about that. In terms of the challenge of going to Mars, at the top, I show you the Earth-Moon distance. As you know, it's on average 400,000 kilometers approximately. And the Earth-Mars distance, of course, changes radically depending on whether or not the Earth is in conjunction or at opposition from Mars. And so when the Earth is closest to Mars, the distance drops to about 140 times the Earth-Moon distance. But when Mars is on the opposite side of the sun from the Earth, then the distance ramps up to about 400 million kilometers. And at that point, Mars is about 1,000 times farther away than the Moon. And this is sort of an interesting consideration because, the lifetime travel delay issue set aside, you are really going to make a big leap in terms of distance from the Earth here by going to Mars. There's no more, like when you're on the Moon, the ability to return within a few days. You can go to the Moon in about 3 days. You can spend as long as you want at the Moon. You can come back anytime. And it's another 3 days. You can leave on a Monday morning for the Moon, get there Wednesday night. You can spend Thursday on the Moon. Friday, you catch a flight back. Sunday night, you're back home. Monday morning, you're back at work. So Earth Moon is something you can do within a week. Mars is not the same thing. It's a very different type of operation. Okay. So in terms of the surface conditions, which is really what you want to be coping with, there are good things and bad things, but I'm forced to do a reality check because we're so attracted to the beauty of the Martian landscape that we often forget how lethal and how unfriendly this place is. And so as much as I am very much an advocate of the human exploration of Mars, I'm not an advocate of the colonization of Mars or the settlement of Mars. And I just find that there's not much sense in having an entire population, living in essentially an intensive care unit at the surface of Mars. On the other hand, being able to explore the place and having trained explorers and even tourists come visit for short term, I can see a big attraction to that. But long-term settlement, we tried that in Antarctica and it didn't work. But anyway, there are good things that are going for you when you want to go to Mars. The day is 24 hours and 37 minutes, so it's close enough. I don't know about you, but I can use an extra 37 minutes per day. Water ice, there's plenty of it. It's at the poles exposed. It's at shallow depth, anywhere from 60 to 80 degrees latitude north and south. And then it's there as well at lower latitudes, only a bit deeper down. And then now we're finding locations where even around 40 degrees north or so, there can be some ice very near the surface. Gravity is not as strong as on the Earth, but it's there. And that's an important thing. It's about 0.3 AG, which means that your high jump record on Earth can be multiplied by 2.7, but when you go to Mars. This is something that actually is interesting if you consider, some sort of an indoor gym, for example, like a basketball court that we could one day have on Mars, or even the ability to bring a dog to the surface of Mars. You'd be faced with an environment with a gravity that's about a third of that of the Earth. And so, to first order, you can jump about 3 times higher than on our planet, and that can be very entertaining. But there are several bad things that are going for you. And I've listed on the right from top to bottom in chronological order of cause of death, the things that will kill you on Mars. The very low atmospheric pressure will kill you within seconds. You would essentially experience the bends, the gases that are dissolved in your bloodstreams right now would essentially boil off if you were exposed to the low atmospheric pressure. And so once again, you would die within seconds from the low atmospheric pressure. This is, of course, if you're unprotected by a spacesuit or habitat. If that didn't kill you, then the atmosphere of Mars is toxic for you. It contains CO2, which is a toxic gas, and you would die within minutes of hypoxia by being just exposed to CO2, not being able to breathe anything else. The temperatures are frigid on average, minus 80 degrees Fahrenheit, so that's minus 63 Celsius. That will freeze you to the bones within about 24 hours, within a Martian day, basically, or Earth day. You'd be completely frozen if exposed to those kinds of temperatures. So that will kill you within hours. If that didn't kill you, the dust on Mars is toxic. It is now known to be replete with peroxides, perchlorates. The movie The Martian has several, well, the movie and the book have several issues with them. Andy Weir actually is a friend, and I often tease him about this, but he's actually fully aware of the issues in his book. His publisher actually wouldn't let him correct them. But the low atmospheric pressure, for example, means that as fast as the winds on Mars can be, they will not really exert any dynamic pressure on you. And so you would essentially hardly feel a breeze, even if you were facing 100 knot winds on Mars, just because the atmospheric density is so low. Same, and with the dust, that's sort of the other issue. The dust in the Martian, you see Mark Watney scoop up tons of Martian dirt, bring in that dirt into the habitat to grow potatoes. Well, that dust actually would be toxic, and in a matter of weeks, you would have thyroid problems, and essentially you would eventually die from exposure to perchlorates. The good news is that you don't actually need dirt to grow food. You just need nutrients and water. And so he really did not need to bring in all that dirt into the cabin. We can talk more about the dust later, but it's also abrasive, and it's also very fine grained. So it will mechanically clog the pores of your lungs. It's essentially Miner's disease or silicosis that you would experience by ingesting or inhaling the Martian dust. Okay, so that's very bad news. And then if that didn't kill you within a matter of weeks, then radiation would kill you over time in a matter of years. And it's sort of odd in some sense that we're so hung up on this radiation thing about going to Mars, because it's actually the thing that will kill you the slowest, generally speaking, unless you were really exposed to a solar particle event. But it's something that might not really kill you or increase your chances of death by cancer by more than a few percent by the time you come back from a journey to Mars. And yet we're so focused on that. And I think it's because there's very little we can do about it that's sort of practical, at least for early missions, to shield yourself from radiation. And so in that sense, it's one of those things that we realize the astronauts will be exposed to that. Everything else you can sort of protect yourself from, radiation you can't. But really, even in terms of risk to an astronaut, the launch is several times more dangerous than death by exposure to radiation over the course of several years. So I'm not quite sure why we're so worried about radiation, generally speaking. All right. Now, why would we want to go to this terrible place? Well, this is my personal favorite reason, which is we are in search for alien life on Mars. And I work at the SETI Institute, and so we're not shy about using the word alien. But this is really what we should emphasize, though, when we're searching for life on Mars. The whole quest, the whole purpose of all these missions going to look for life on other worlds is to find an example of alien life, okay? We now know that the planets are not isolated systems. The Earth and Mars have swapped rocks. Impacts, as you know, take place everywhere. When asteroids and comets, the large ones, hit Mars, pieces of Martian rock fly into space. Some are hit the Earth. We collect them. We have Martian meteorites in our collections. And similarly, there must be Earth meteorites sitting on Mars today. So it's a bit of it wouldn't be surprising if microbial life were able to hitch rides both ways over time. And therefore, if life ever did pick up on Mars, it could actually be the same kind of life as life on Earth. What you have on the left here is known as the tree of life. You can think of it as a tree where the closer you are to somebody else or something else on this tree, the more DNA you share in common with it. For those of you who are biologists and sort of sticklers, this is technically a 16S ribosomic RNA tree of life, not quite DNA. The RNA essentially is more transmissible stably through generations, and so that's why we use it for phylogeny, for these types of genetic trees. But the point here is that all life on Earth uses DNA. All life on Earth shares DNA in common, and the degree to which you are sharing DNA in common is essentially reflected by the proximity you are to other forms of life on this tree. And the straightforward interpretation, actually, of this commonality in the usage of DNA is that we all come from a common ancestor, which, of course, no longer exists in the fossil record, but is the cause of everything that is living here on the Earth today through mutations and evolution over time. What we're looking for on Mars is an example of a separate origin of life. What we would like to find is an organism or trace of it that would not fit onto this tree of life, that would represent a separate tree of life, even if it were a lot less developed. Think of a little plant of life, but something that would be distinct from life on Earth. It would either not use DNA or use different acid bases, but still sort of have DNA as an overall structure. But essentially, we are, that's what we are after. And that brings me to essentially a friendly criticism that I sort of throw to most missions we've had to Mars today that are focusing on the search for life, which is that even if we found a massive outcrop with fossils and fossil bones jutting out at you on Mars today, we wouldn't be able to tell if it's alien life that we found. You would be able to tell that you found life. You'd write a paper and try to get it accepted in Science or Nature, but you wouldn't be able to tell if it's really alien life. For you to determine that you found an alien form of life, you have to do genetics on it. You have to show that genetically it does not fit onto this tree of life on the left here, the tree of life of Earth, that it's part of a separate tree of life. To do genetics on anything, it has to be living. It has to still be alive today or dead for not a very long time, not long enough for the DNA to be destroyed. And that's a tall order. That means that instead of focusing on the search for ancient life and fossils potentially, we really ought to be focusing on the search for extant life, going to places where there is liquid water today, where it might be clean enough for life forms to thrive in it. And that means going down, drilling. And there's an easier way, of course, to go into the interior of Mars, which is through volcanic caves and lava tubes. And so just for what it's worth, I would recommend that we focus our future searches for life on Mars in the direction of finding extant life that's still alive, for this to make sense. Let me keep going. So there are many other reasons why you would want to go to Mars, and I don't want to spend my whole talk discussing all this, but I have on the left here a long laundry list of reasons that have been proposed as to why we should go to Mars. It captures many people's ideas, including Elon's becoming a multi-planet species. I have a bunch of quotes here. I just want to say that I've been offering $1 to anybody who comes up with now a new reason that's not already captured in this list, but still makes sense. So a few years ago, I was giving this talk part of this talk in Australia, and somebody raised their hand and said, hey, what about establishing a new colony of prisoners and convicts? So that's the last item that I had to enter in this list. I tried to make the case that it was captured already in store waste, but that didn't go too well. So anyway, that's the list. But the point to understand here is that none of these reasons alone are good enough for us to justify the taxpayer cost of sending humans to Mars. And if you look back at the history of exploration, the only thing that has compelled governments to push and pay for expensive missions of exploration is when there was a strategic national interest that was served. Lewis and Clark weren't sent out west by President Jefferson because he was interested in wildlife. He was, but that's not the reason why, at great cost, Lewis and Clark were sent out west. It was to find trading routes, period. Trading routes, see who was living out there and whether or not we could get along. There were many things at stake strategically for the young United States. Same thing for President Kennedy. He didn't send us to the moon in the mid-60s because all of a sudden we were interested in lunar rocks. It was because, of course, we had to beat the Soviet Union and communism. And sure enough, that was achieved finally with the Apollo landings. But again, the key thing to realize here is that we didn't go to the moon for science. Science is what ended up dominating the activity we conduct at the moon, okay? But we're not there because of science. And it's even reflected today very glaringly in the polar regions, which I'll talk about in a bit. Antarctica, for example, the NSF spends about $2 billion a year supporting Antarctic stations. We are not in Antarctica because of science. We are in Antarctica because it serves our strategic national interest to be there. And the other countries that can be there are there for the same reason. Once you are committed to being there, what dominates your activity is science, but it's not why you are there. And that's really important to understand. So it's going to be the same thing with going back to the moon. We're going back to the moon not because of lunar science, but because it will serve our strategic national interest to do so. And of course, once we go back to the moon, you're not going to open a law firm or bank branch. You're going to do science. And so that's why we're so focused on getting good lunar science done. Now, there is a big return, though, from doing things like the Apollo mission and then going to Mars. I like to show this plot because at the bottom, you see the years of the past century, and on the bottom scale, on the x-axis, you see the years of the past century. And on the vertical scale, you have the number of graduate degrees awarded in US universities, okay? And that's masters and PhDs. And we're tracking 4 fields of science: engineering, math, 4 STEM fields, I should say: engineering, math and computer sciences, physics, and earth, atmospheric and ocean sciences. All 4 curves ramp up exponentially to the right. That has to do with population growth. That has to do with population growth in the United States. But what's remarkable are the spikes that you see from the mid-60s to the early 70s. There's a doubling of the number of graduates in these universities in all 4 fields of science shown here. And that is correlated with the Apollo program. The Apollo program was a huge stimulus that got a lot of young people interested in science, technology, engineering, and math. It totally refreshed the STEM force of the nation. And the argument that I usually make to why we should go to Mars is because it would do the same thing to the next generation of kids who would experience us going there. And that is a huge benefit because we're still riding today on that Apollo generation that got so enthralled by science and technology, and that has been allowing the Jeff Bezoses and the Elon Musks to sort of keep pushing ahead with technology and our space program. Now, what about going to Mars now? This is a map of the Earth where NASA and nonprofits like the SETI Institute and the Mars Institute have been doing field research over the years. And this is essentially a partial map of the terrestrial analogs commonly used by NASA, especially as Mars analogs. And you'll notice that all these places are extreme in one way or another. The Altiplano has extreme UV exposure. The Atacama is extremely dry as a desert. The Namib has amazing sand dunes. The Sahara is extremely sandy. Australia is extremely sandy as well, but red. we go to Devon Island up in the Arctic, which you see there west of Greenland, Iceland, Spitsbergen, but also Antarctica, because these places are extremely cold and there are a number of things that happen when the climate is so cold. There's also places like Hawaii, okay, where it's extremely pleasant. Joke aside, of course, we go to Hawaii because it has shield volcanoes, which are very similar to the volcanoes we find on Mars. And Hawaii, of course, is also a place where Apollo astronauts trained, in addition to the southwest of the US, in preparation for their mission to the moon. They also went to Iceland. But today I'm going to focus on Devon Island up there in the high Arctic. And I want to tell you more about this place. So here is where Devon Island is. You go into Canada and past the Arctic Circle. You're now farther north than even Point Barrow, which is the northern tip of Alaska. You go all the way to 75 degrees north and you get to Devon Island. Devon Island is the largest uninhabited island on Earth. It's about the size of West Virginia. So it is even less populated than West Virginia. It is home to a large meteorite impact crater, Haughton Crater. And what you should also realize is that Devon Island is the largest continuous expanse of rocky polar desert on Earth. Polar desert is a very specific type of climate on Earth. You're used to thinking of tundra when you're thinking of Alaska or Siberia. That's cold, but it's relatively wet still, and you have grasslands essentially in tundra. Taiga, of course, is even a bit warmer. You even have this evergreen trees like pine trees. The bulk of Canada is taiga, so is the bulk of Siberia. But here on Devon Island, you're so far north, and the climate is not only cold but also dry, that you are entering the realm of the polar desert, where again you don't have trees anymore, at least nothing nothing huge, and trees are reduced to ground hugging little plants that sort of defy the definition of a tree. And yet they are trees, but they're very small. So where's Devon Island? Well, it's in the high Arctic, but the closest community to it is Resolute Bay, which is on nearby Cornwallis Island to the west. And that's how we get to Devon Island. We fly an airliner into Resolute Bay, and then from there we usually wait for the weather to get better again. And then we fly from Resolute to Haughton Crater, where we have a camp and an airstrip that we've set up next to our camp. Okay. Now, in terms of the geopolitics of it, Devon Island is in a territory of the Canadian high Arctic called Nunavut. And Nunavut used to be part of the Northwest Territories, and it's in the old definition of the term Northwest Territories, but now the Northwest Territories are reserved to the western part of the high Arctic, and now you are looking at Nunavut for where Devon Island belongs. I should also point out that running through the waters around Devon Island, this maze of islands and waterways are what are known as the area of the Northwest Passage. And there are still some disagreements between the United States and Canada and a few other countries about who owns the Northwest Passage. The US's position is that the Northwest Passage are international waters. The Canada's position is that the Northwest Passage waters are Canadian waters. So I just wanted to give you a bit of context here. And the entrance of the Northwest Passage on the eastern side is usually recognized as being the channel that's right south of Devon Island, called the Lancaster Sound. Now, a bit of geology really quickly. This is a beautiful geological map of Devon Island. And one thing to notice is that on the eastern half of the island, you have a large ice cap that's still draping the rocks, but the rest is exposed rocks. And you can sort of see a hint of north-south banding in how these rock units are laid out. And that's because the geology of Devon Island is actually relatively simple. Think of it as a wedding cake, if you will, that is tilted a little bit with a knife that would have cut the top surface of the cake sort of at an angle. And now you see the different layers showing up as bands that are running parallel to each other in a north-south direction. So I've created a section for you. Imagine you cut down into Devon Island along that red line that I just drew. And this is what you would see underneath the surface. Okay, so beneath the Devon ice cap, you have these light pink rock units, which are very ancient crystalline basement rocks made of granites and gneisses. And then sitting on top of this, a tilted stack, if you will, of ancient marine seabeds. So the light green layer, the dark green layer, the orange layer, the gray and the blue layers, all of these are ancient marine seabeds. The ones that are farther away from the pink are younger. The ones that are closest are the oldest. And so if you were to walk along this line that I've drawn across Devon Island there at the top, let's say from east to west, you would be walking, first of all, on an ice cap, and then eventually you would get to rocks that are about 500 million years old. And then as you walk farther east, you get into rock layers that are younger and younger. Okay, so it's an amazing place to explore. You are sampling a huge window of time here in the history of the Earth. Some of the youngest rock layers on Devon Island are actually, actually it dates back to glacial processes and from about 10,000 years ago. But in terms of proper rock layers, some of them are as young as about 40 million years. Okay, and Haughton Crater, which I'll get to in a second, is even younger. So a few things to note about Devon Island. You will find fossils or examples of the very first trilobites that ever roamed the seafloor of the Earth. Trilobites reigned on Earth for hundreds of millions of years. They're a very robust type of early life form on Earth. Trilobites are very common in marine seabeds from the Paleozoic. Here on Devon Island, you have examples of some of the very first ones that appeared in the history of life on Earth. And then we also have later in the stack, so more towards the east along that line I just drew, including at our base camp, which I show here in the top image and the bottom one as well, we are into 460 million year old rocks. And these were ancient coral reefs. Corals were not common yet. The reef was made mostly of cyanobacteria, but you are looking at the very first tropical reefs that formed on Earth about 460 million years ago. And ironically, our camp is sitting there. Now, what you have in the lower image on the left is in the foreground, you can see this brain coral in the rock, and our base camp a little further up there. Time went by, so the stack of marine seabeds eventually got exposed. So 170 million years ago, Devon Island was underwater. It wasn't an island yet. 100 million years ago, it was still underwater. And then about 70 million years ago, Devon Island started rising above the waterline. And today, of course, it's an island. And over time, it has been migrating from the tropical regions of the Earth to the Arctic. And about 23 million years ago, something incredible happened. Not uncommon in the history of the Earth, but something that still has left a scar visible today, which is the Haltom impact event. We don't know if it happened during the northern summer, in which case it would have been daylight all the time, or in the middle of the northern winter, in which case all of this would have happened in pitch darkness. But a giant impact took place, and the impactor was approximately 1 kilometer in size, so about half a mile in size if it was traveling at, say, about 15 to 20 kilometers per second. And it excavated within a few seconds. So it took about 10 seconds to excavate Haughton Crater as a sort of a bowl in the landscape. It excavated this gigantic basin. Well, I shouldn't call it a gigantic basin. It's a medium-sized crater as craters go, but it was pretty big compared to say smaller things like Meteor Crater in Arizona. And so Haughton Crater formed about 23 million years ago and then ended up being about 20 kilometers in diameter. Okay, so that's what we're looking at here at the bottom. That's Haughton Crater, the bullseye, seen from an altitude of 10,000 feet. Now, note that this painting, which is by Mark Carroll, space artist, depicts Devon Island as being vegetated, and this is correct. At the time, in the Miocene, 23 million years ago, all of the Earth was quite a bit warmer than it is today. And not only were there trees and evergreen trees like pine trees, there were also deciduous trees, trees that would lose their leaves in the winter, and that's portrayed here. Shown also are these giant rabbits of the Miocene that are, I guess, running away from the supersonic shock wave. I'm not sure they would have made it, but there you have it. Now, this is what geologically the Haughton impact event did to the landscape, to the geology. It essentially, well, on the map there near the top, you have Haughton Crater as a sort of a circular structure, but then in section there, I'm showing you with some vertical exaggeration because it's not really that deep, but the vertical exaggeration shows you how the bottom of the crater actually still managed to hit the pink rocks, if you will, of the crystalline basement of Devon Island. So that today, when you walk at the surface of Haughton Crater, you can pick up bits and pieces of granite and gneisses that have been excavated from about a mile of depth at that location. So it's quite incredible to have this kind of geological event and sampling for you done by nature. And so if you go there to Devon Island, to Haughton Crater, or if you take astronauts to train them there, you can train them to look for things like lunar mantle rocks once they get to the moon, or things that have come from layers that are far deeper down than layers that are normally found at the surface of the moon. Okay. So following the impact, the crater was occupied by a lake. There were animals around. Mary Dawson, who's a famous Canadian paleontologist, has recovered remains of a small rhinoceros on the shores of this lake that once occupied the crater. And then also an important discovery was made just a few years ago, not by our project, but by paleontologists from the Canadian Museum of Nature. They found the missing link between land mammals and seals at the time when seals and related creatures are called pinnipeds. And pinnipeds, as you know, a bit like whales, were once land mammals that eventually went back to the sea. Well, we were missing the missing link between land mammals and the first seals. And the first example of that missing link was found in the lake beds inside Haughton Crater from that lake that once occupied the crater shortly after its formation. So the lake beds of Haughton Crater actually are quite unique. They are one of the few records of the Miocene in the Arctic. In fact, the only record of the Miocene in the Arctic anywhere on Earth that's still preserved. And then Devon Islands continues with an incredible connection with the history of exploration and life. About 3,900 to 3,600 years ago, Inuit, or at least early Arctic people, were already occupying the Arctic. They started as as populations that fed off the land first, and then eventually at sea. But at one of the archaeological sites on Devon Island, this little figurine was found, and it is now considered to be the oldest human portrait from the Arctic known on Earth. And then again, it's from about 4,000 to 3,600 years ago. And we think that we're seeing tattoo markings on this figurine's face, which are reminiscent or similar to tattoo markings that we see on the faces of elder Inuit people from the north who were alive even in recent times. So this lady on the right was photographed earlier last century, and she bears tattoo markings that are similar in some sense, or reminiscent at least, of what was found on this figurine. The Vikings also have left a mark somehow on Devon Island. We don't think that they actually went there, but there's an archaeological site on the west coast of Devon Island that has a piece where a piece of Viking pottery was recovered. And so the thinking here is that the Vikings, of course, traded with Arctic people of Greenland, but also presumably of Baffin Island. And eventually some of their artifacts got scattered across the Arctic and all around Baffin Bay. which is the big embayment here between Baffin Island and Greenland. And then eventually, of course, the Northwest Passage was a big adventure and search. This is the Europeans, of course, trying to find a seaway across the Arctic that would create a shortcut essentially between the Atlantic and the Pacific and facilitate trade. It turned out to be, of course, a disaster. There's no practical Northwest Passage, at least. It might be opening up now with global warming, but for all these past centuries, it was essentially wishful thinking. And in recent years, we finally found the two ships of Franklin much farther south from Devon Island. But Devon Island is where some of the first deaths were recorded. And I show you at the bottom here on the third picture on the right-hand side is showing you 3 graves of sailors of Franklin's expedition, among the first who died during his expedition, his ill-fated expedition, which led to the loss of 128 souls on 2 ships, including the commander. They had to resort to cannibalism and all kinds of horrific means of survival. And of course, none of them actually survived. So Mars, here we are back to Devon Island, these forbidding shores, now again with a history of exploration, but looking to the future and how this place might prepare us for Mars. This is Mars. This is what the landscape of Devon Island looks like. And we are very interested in this place. I'm going to show you a series of image pairs where on the left you have Mars and on the right-hand side Devon Island. Because it's geology and you're an astronomical society, I'm not going to go into a lot of geological depth here, but suffice it to say that we are really intrigued by so many similarities existing between Devon Island and Mars, and we think that there is actually a common cause, of course, to some of these geologic features. Here are 2 craters on Devon Island and Mars that are similar in scale. We know the age of the one on Devon. We know what the climate has done on Devon, how much it has rained there, for example, since the formation of the crater. We know the size of the crater on Mars. We know roughly how old it is. This allows you to constrain how much raining has happened on Mars over time, what the climate has done since the formation of that crater on Mars. And as it turns out, Mars, of course, has been much drier and presumably colder than Devon Island. But this has been helping us dispel the common notion that Mars might not ever have been warm and wet as you might often hear. Okay. But I'll get back to that in a second. There are ground ice features that are very similar between Mars and Devon Island. There are rock glaciers that we think are what we're seeing here on Mars that we find on Devon Island as well. There are sapping valleys that grow in the direction of their source by eating their way into the land. And there are these valley networks, which we've first reported that on Devon Island, the ones on Devon Island look really very much like the ones on Mars. The ones on Mars have historically been attributed to a warmer climate in Mars's past, the assumption being that it had to rain on Mars for these finely chiseled valleys to be incised into the Martian landscape, when in fact on Devon Island we've shown that these guys, which are very similar in morphology and scale, these guys are formed by the melting of former ice sheets, and they were formed underneath ice sheets. They were not due to climate warming or raining. They were due to the ground being warm enough for these things to melt. And we think that is sort of we think that that's actually what has happened on Mars. So on Devon Island, it was a combination of the ground and the climate being warmer that led to the melting of these ice sheets. But on Mars, it likely was only the ground being warm early in the planet's history from volcanism and impacts. So what you're looking at are probably on Mars the valley networks that were formed underneath former ice covers that were so cold that they did not really create moraines or did not move around too much. They were just ice that was sitting there. On the young planet, however, the ground was warm, again, from impacts, from volcanism, from a higher geothermal gradient, so a higher heat flux coming out of the planet itself. And that would have led to the formation of these valley networks on Mars. So not at all telling us that the climate was warm on early Mars. If anything, the climate could have been as cold as it is today, telling you only that the ground probably was warmer than it is today. Canyons as well are similar on Devon Island to some of the ones we see on Mars. The ones on Devon were carved by glaciers. We think that these guys that we're looking at on Mars here on the left are also formed by moving ice in very limited locations on Mars in the past. And then we have the gullies of type 1. We see examples of those. I want to point out that somebody's waiting to be admitted. Gullies of type 1, gullies of type 2, and gullies of type 3. So a wide array of gullies, all of which seem to have counterparts on Mars. And so we're very intrigued by this. And we think that a lot of these are actually associated with the melting of either surface deposits of ice or ground ice, okay, from the summer melting of the permafrost. So all of this makes sense. And again, it goes back to why we call this place Mars on Earth. Now, there's also life. I'm moving away from geology now, a little bit of biology. There's life. This landscape that you see, it's actually teeming with life, but it's teeming with microbial life that's hidden inside rocks. If you slice open a rock, like I show on the lower left, you'll see a little rind of green underneath the surface, about 1 millimeter underneath the surface. That's a colony of cyanobacteria that's living in the nooks and crannies of the rock, just into the rock enough to be shielded from the UV, from the wind, from the cold and the dryness, but not so deep that they cannot have the benefit of sunlight. These green colonies of cyanobacteria, of course, are plants, so they photosynthesize. They're unicellular plants. And so there you have it. These cyanobacteria essentially doing what caveman and cavewoman would do, which is to hide in the shallow recesses of caves, okay, where you're sort of in the twilight zone. Cave dwellers never really spent a lot of time deep inside caves where it was dark and cold. Instead, they were sort of in that twilight zone where you were sheltered, but at the same time had the benefit of daylight nearby. And of course, there's the polar bear, which is irrelevant, we hope, or we think, to exploring Mars. This is a view that I shot actually while we were flying a helicopter, and all of a sudden this patch of snow started to move. Sure enough, it was a polar bear. So polar bears, of course, are at the top of the food chain in the Arctic, and we need to be very careful because they travel fast. They really own the Arctic, land and sea. They will cross Devon Island within a matter of hours, going from one feeding bay or seaway to another. And so, they really are the ruler of this place that you have to look out for and not cross paths with if you can avoid that. And so we have dogs for this as a polar bear deterrent. The dogs, as you can see here, on threat level alpha, they are essentially looking out for polar bears and sniffing them out, we hope. And since we're not entirely sure that these dogs are always enough, we also hire sometimes high school teenagers from nearby Grise Fjord or Resolute Bay, the two closest communities to Devon Island, where we have experienced kids dealing with wildlife and carrying rifles to keep us safe. So this is literally a NASA project that is protected by armed teenagers. All right, I want to talk to you about our base camp. This is our base camp. It's a permanent camp. We leave it up year round. Although it's not there forever, it's still just a series of tents and some, wooden and shacks, but it's been holding up pretty well. We set this up in the year 2000. And here we are, 21 years later, and it's still up and doing mostly okay. So just to give you a map of the layout of the place, you have the airstrip on the left, the upper left, our fuel depot, an incinerator where we burn our usable trash, our burnable trash, a helipad, a fortress, which is just a natural feature. It's actually a reef, an ancient reef. Imagine all this sort of under tropical waters 460 million years ago, or 430 million years ago. And then our base camp at the lower right with a trail that we've created called NASA Road 1. For those of you who are familiar with Houston and the Johnson Space Center, you'll appreciate the naming of this feature. So this is our base camp. It's in the star formation. It has a core, which is a sort of a logistics hub and a social hub for us. And then different tents have, of course, different functions. In fact, we've been studying our use of space, our use of our layout of research stations. We've actually never really done any simulations of a crew on Mars yet at this facility. We just do what we need to do to have a productive time doing research in the Arctic. But nevertheless, you learn important lessons from the practices that you use to stay safe, to separate the functions that you need to perform inside these tents. Some labs are devoted to astrobiology, others to geology, others to comms, others to just general maintenance, etc. So here are some of the functions. You can see that we don't have to go into all these details, but we have a workshop and a garage on the far left. We have a fleet of vehicles, 13 ATVs, a couple of Humvees, side-by-side vehicle. And then we have a greenhouse that's separated from the rest because the greenhouse needs to take advantage of the sun going around the sky, sort of in a full circle. So you don't want to be hiding the greenhouse or shadowing the greenhouse with your other buildings. So that's why it's set aside. It has its own solar power grid, if you will. There you have it. So just a few views of camp, the core, the inside of the core, sort of a nice rustic feel. Nothing beats wood still in terms of durability in the Arctic and Antarctic. So this has a, but this is an important storage space for us and also a social area. This is our office tent where we hang our latest spacesuits. These are analog spacesuits from Collins Aerospace. This is also a map room where we plan our road trips, our traverses in the field. So this would be the mission control room, if you will, of our camp. We also have an astrobiology lab where we have some equipment like centrifuges and incubators. And then, of course, we have the medical tent, which can be connected or serviced by a Humvee. We have 2 Humvees at camp. They are essentially formerly military ambulances, and in a contingency, we could bring back an injured person inside one of these Humvees, using it as an ambulance essentially, and docking it to this medical tent, where we could then provide some first aid care. So this is the inside of the medical tent. It's very basic. We do have some equipment that's not shown, but essentially Devon Island is a place where you don't want to get injured in the first place. So we have a lot of safety rules. Over the past 25 years, we've had over 10,000 person hours or person days of operations there, and nobody's ever had a serious injury that they didn't recover fully from. So that's like they say at the FAA, no accident is no accident. We emphasize safety a lot. There are safety briefings before, during the mission, and even after. It's a very safety-minded type of field operation. And of course, it needs to be like that. Storage is going to be a huge problem. There's one lesson that I'd like to share about a future base on the moon or Mars is that storage is going to be underestimated. You're going to need more storage than you are planning for. And storage is essential because even if you don't occupy a place constantly, you don't always use everything at the same time. And you're going to need to store your assets, your equipment properly, organize it well to have access to it down the road. So here we are showing some external storage, an external storage rack, items that do not mind being in the elements, because the indoor storage space is, of course, at a premium at our camp. Here's the greenhouse, which was contributed by spaceref.com, and it was used very productively by a research team from the University of Guelph in Canada and also the Canadian Space Agency for several years, 6 or 7 years, and they finally achieved a milestone, which was to run this greenhouse robotically, autonomously for an entire year, including when we were not there in the middle of the winter. And so all of this is published. You can refer to the literature about this, but this is our Arthur Clarke Mars greenhouse on Devon Island, and its solar power station. Now, a few notes: we don't go to the bathroom anywhere on the ground, at least not at camp. We have to be very mindful of protecting the environment, not just for environmental stewardship, but because we actually would be altering the environment in a way that would get in the way of our science if we just went to the bathroom like this at camp without precaution. So what I'm showing on the left here are the men's room. These are empty fuel barrels. Now they're equipped with a funnel. There's a little cooler that you step on to step up to the occasion. And you just go for number one outdoors like this at the edge of our camp. If you went to the bathroom anywhere at random on the ground, the urine that you produce would enrich the soil in the Arctic here in nutrients that it normally doesn't have. And so you would enrich the soil in, say, nitrogen and phosphates as well. And that is something that that would promote plant growth. So just to show you how an input of organic material into this Arctic soil can really alter the environment, I'm showing you on the right here a fox, the remains of an Arctic fox. It might have died 50 years ago. It might have died 400 years ago. We don't know. But its remains, its organic remains, have seeped vertically into the ground. And now, instead of an animal with flesh over its rib cage, you're seeing a colony of moss growing and taking the shape of the body of the fox. And that is essentially the organic material of the fox turning into a little colony of moss. Okay, so we think it was a bad fox because it reincarnated into something pretty primitive, a patch of moss. Anyway, we could also use this camp in the winter, but we don't so far. We haven't. It's a matter of budget, really. But in case you are willing to sponsor us for all winter campaign, we are good to go. We are set up for that. And we think that in the future, astronauts will possibly come and train for a few months at a time, or at least a few weeks to possibly a few months at a time, and really operate the station as if they were at the Artemis base on the moon. And see what it's like. The lessons we're learning, we hope, will translate into lessons for future Mars base. And let me talk to you a little bit more now about human exploration. But before that, a few robots. We've had robot rovers over the years. On the left, you have NASA Ames's K-10. On the right, you have my little K9 unit. She is a little shy. We've also tested a number of robotic flyers. This is a recent one that we've tested, the Mars Electric Reusable Flyer from NASA Glenn Research Center. It's a vertical takeoff vehicle, but then it tilts over and flies horizontally like an airplane would. So it maximizes performance for horizontal straight and level flight, and then also maximizes or has the advantages of vertical takeoff and landing for handling very rough terrain and not having an airstrip for landing. So it's a hybrid, if you will, flyer. We've also been testing robotic drills over the year, and this is largely an effort led by NASA Ames's Dr. Brian Glass, who is a automation expert and has been developing various software technologies that will allow us to drill on Mars, are allowing us and will allow us in the future to drill on Mars and get deeper and deeper, and hopefully finally reach extant life, which is, of course, in my view, what the holy grail of our search for life on Mars. And then lessons for humans more specifically. We've been working on the spacesuit. The spacesuit is a big deal. The spacesuit that we have right now, the state-of-the-art suit at the station, for example, weighs 300 pounds or so. That is way too heavy. If you take that same suit to the moon, not that it's designed as a walking suit, but let's say you gave it the joints that it needed for walking. On the moon, where gravity is 6 times less, 300 divided by 6 means that you're carrying a 50-pound suit. That is relatively manageable The Apollo astronauts wore a suit that was in the 240 to 230 to 240 pounds or so. And so that had a felt weight of about 40 pounds. That was quite manageable. If you take the same suit to Mars, where gravity is 38% of what it is on Earth, a 300-pound suit would have a felt weight of 125 pounds. So that is way too heavy for you to walk around. What we need to do essentially is bring the mass of the current suit down by half, okay? In order to have a suit on Mars that would weigh not 125 pounds, but something like maybe 60 pounds as a felt weight. That would still be heavy, but it's a huge challenge. A spacesuit is already lean and mean. As you know, it's not just clothing; it's a wearable spacecraft. And right now, the challenge we face again for a Mars suit is to bring the mass of this wearable spacecraft from 300 pounds to about 150 pounds. That's the weight on Earth. So that on Mars, it would have a felt weight of about only 60 pounds. We're not there yet. And for those who say that, we're ready for Mars anytime, it's just a matter of political will. Well, there are a few things that need to be worked out still technologically before we're going to be useful explorers on Mars. And one of them is to bring the mass of the spacesuit down. So if some of you out there are interested in becoming aerospace engineers, I would highly recommend going into, if not rocketry, going into EVA suits. There's a beautiful job that waits to be done here in the aerospace industry on the Mars suit. So we've been working with Collins Aerospace, formerly known as United Technologies Aerospace Systems, formerly known as Hamilton Sundstrand. They have been the providers, or actually the contractors for NASA for life support systems since the Apollo days. And with them, we've been working every year now, pretty much in the Arctic, every summer on a design for future Mars suit, a design that would lighten the suit to the extent possible. In addition, we need a suit that can do things that we've never done before with spacesuits, like possibly rock climb. Mars has canyons, they're very interesting. We might not be doing rock climbing every day, but it's a capability that we definitely want to have down the road, at least for our spacesuit. And so you want to be able to do something like this, maybe at some point, to explore outcrops along canyon walls on Mars. So in the end, our suit might end up looking like this, something that is relatively lean and trim. This is an example of a rear entry suit. So you get into the suit through the backpack. The backpack swings open like a refrigerator door. You climb in, legs first. The legs go all the way down to the boots. Then you insert your arms, and then you or somebody else helps you close the backpack behind you, and then you are now sealed and pressurized, and then off you go. Okay. So, but you can still only go so far with a spacesuit on foot. You're going to need a mobility system. And on the moon, on Apollo, we weren't going very far from the lunar modules, and so an unpressurized rover was sufficient. This is the beautiful Lunar Rover, 3 of which flew to the moon on Apollo 15, 16, and 17. And this Lunar Rover, by the way, was not built by GM, but by Boeing, and it was an electric rover. Now, it was the right solution for Apollo. They were not on the moon for very long. They really had to stay together as a buddy pair for exploration. And they were very limited in mass, given that they were only going one time to each site. So therefore not building up an infrastructure. And therefore it made sense to have a buggy that could carry 2 astronauts at a time. So this is why we did the Lunar Rover the way we did at the time. But for Mars, you're looking at much longer stays, greater range. And forget about Mars even for Artemis in our return to the moon, we want longer range, farther exploration. And so we've been advocating the use of a personalized ATV as a better basic mode of locomotion. So the lunar or Martian ATV might be a little larger than that, and carry a few, additional systems and supplies. But the idea here is to have each your own mobility system. That adds a lot of flexibility and redundancy to how you operate. So a design might look like this. Don't worry about sort of the design details. The concept here, though, is that while you're writing, you can offload some of the heavy, while you're writing, you have offloaded some of the heavier items in your backpack, like the oxygen tanks, the water supply, the batteries that are normally taking up a lot of weight and space in your backpack. You've offloaded them onto the ATV. And so the ATV is essentially what allows you to recharge your backpack while you're riding. You can recharge the batteries and therefore carry smaller batteries in your backpack. You can recharge the water in particular, and therefore carry less water in your backpack in the first place. And of course, if you step off of your ATV to go pick up rocks, this thing is a smart vehicle. It's self-driving. It will follow you. You don't have to walk all the way back to your Lunar Rover, for example, to drop off your rock samples. You just turn around and your ATV is right there. So we're looking no longer at an astronaut as a single individual, as an exploring system or exploring unit, but the astronaut and his or her ATV as the exploration unit. And then, of course, no astronaut would still go out alone. And so you would envision two ATVs working in tandem, at least, two astronauts working together, each with their own ATV. And in case one breaks down, well, you can, the other astronaut can ride back. You just get rid of this trunk, this case in the back, which is spare parts, and you sit facing rearwards. The second astronaut sits facing rearwards and plugs in to the same ATV extra supply of batteries, water, and oxygen to get back to safety. For longer road trips, we would use a pressurized rover. And on Devon Island, we have two Humvees helping us do mission simulations or concept simulations with rovers, with these pressurized rovers. At first, we only had one Humvee, which, by the way, we drove from Resolute Bay to Devon Island on sea ice in the winter. That went actually really well. So when we needed a second Humvee, because we were tending to get the one Humvee stuck sometimes, we wanted a second one to be able to rescue it so that the two vehicles could work in tandem. We decided to drive the Northwest Passage. And so this is the second Humvee that was donated to our project by AM General, the maker of Humvees. The first one was a military vehicle that actually had seen the war. It was flown back from Iraq at some point and got transformed into our first pressurized rover simulator by AM General. And then the second one actually was yanked from Hollywood, where it had never seen battle. It had spent its whole life in movies, basically. And since we're in the Bay Area, this is the very Humvee in which Nicolas Cage retrieves Sean Connery out of Alcatraz out of retirement to ask him to help them get to Alcatraz. Anyway, they have a conversation inside this very Humvee in the movie The Rock. And now this Humvee is on Devon Island and painted yellow. So to get the second one to Devon Island, we decided to be a little bolder, and we drove the Northwest Passage on sea ice in the middle of the winter. So it was a seafaring expedition, only on solid sea. And that turned out to be epic, more epic than I probably would have wanted. But I won't tell you if we made it or not, I guess. But if you want to see or experience our journey, including the boredom that came along with it and the moments of panic as well, or at least of intense terror, you can watch this movie, Passage to Mars, which is a documentary, a motion picture documentary on our expedition to get the second Humvee up to Devon Island. Now that the two vehicles are there, we use them as pressurized rover simulators in some applications, or simply as transport vehicles. Here you're seeing an astrobiology lab essentially deployed inside the rover so that the samples we collect can be analyzed immediately. So this is actually an interesting concept where we use the rover as a temporary outpost where we might do some field studies in a local area that's away from our base camp. And we spend a few days in this Humvee, do the science on site so we can iterate depending on the results we find, and then do further sampling and then come back eventually after a few days. So we think that the pressurized rovers of the future should have some analytical capability like of the kind that we were using. Of course, more compact, more integrated, but nevertheless, in principle, the same thing. And of course, we are getting ready to get back to the moon, which is a very diverse object. I love this image, this composite image from a spectrometer on the Galileo spacecraft, which was on its way to Jupiter, but did an Earth and Moon swing by. And it acquired this beautiful image of the moon showing its geological diversity. So the moon looks perhaps dull and gray to us with the naked eye, but it's really an incredibly interesting world with lots of history and a complex history, actually. And we're returning there now with Artemis. So Devon Island, we think, will play a role in this return. This is the moon on the left, Devon Island on the right. So if you wear your black and white sunglasses, you can feel that you are on the moon. And of course, Haughton Crater, as it turns out, is exactly the same size as Shackleton Crater, which is at the south pole of the moon, and possibly one of the targets for the Artemis missions in the years to come. So we think that by going to Haughton Crater, astronauts could get a good sense of the scale of exploration at a site like this, and sort of learn operational lessons for their journey on the moon. We are also using Devon Island in a broader sense beyond the crater as an exploration zone and testing concepts for how long it would take us to explore a region, what types of, how much sampling would be done, what types of logistical issues might come up. All of these things are done best by doing them and learning the lessons that apply to the moon or Mars as you go about doing them. So projected on this map here are two circles. The solid circle is the 100-kilometer range circle from our base camp. The dotted red circle that's wider is the 200-kilometer range. And so these are called exploration zones. It's a concept that was proposed by Steve Hoffman, Ben Bussey, and Rick Davis at NASA headquarters. Steve Hoffman is at NASA Johnson Space Center. And these exploration zones are interesting because they are, of course, notional. Roughly 100 kilometers is what we might think a crew might get to explore, reasonably quickly with pressurized rovers over time at a fixed base, out of a fixed base on the moon or Mars. And so we're really doing that now. We are going out on these road trips with our Humvees and trying to see how far we get and what are the operational lessons we can learn from these types of excursions. And then we're also developing new technologies for the future spacesuit. And I'm going to end here. The Astronaut Smart Glove is something that we have just begun testing. We are envisioning a return to Devon Island this summer, where we will test a new generation glove, a new generation suit, information technologies from Collins Aerospace integrated to the spacesuit. Also, we will be performing experiments for the Office of the Chief Medical Officer at NASA headquarters, in particular, measuring some of the physiologic exertions of astronauts hiking around in a suit over landscape that is similar to what will be encountered on the moon, and getting some baselines, some terrestrial baselines for these kinds of long walking EVA efforts. Anyway, a lot more to come. Leading, we hope, down the road to the training of astronauts, both NASA and private sector astronauts who might be bound for the moon, and eventually Mars someday. So we think that Devon Island has a great future, and this is just the beginning. So this is actually my dog, my previous dog, King Kong, happy to see me at the end of an EVA ATV test. But King Kong passed away, so now I have Apollo. So I'll just leave you with this. And if we have time, I'd like us to watch maybe the 7-minute video called Astronaut Smart Glove, and then I can take questions right after this. And sorry, I probably blew the schedule, but thank you for staying.
Pascal, if you'll, okay, good, thank you. I'll start the video.
Well, thank you for staying. I'm sorry I blew the schedule, but
Okay, so folks, thank you very much, Dr. Lee. And what we would like to do now is take questions. And so the way this is going to work is if you look at the bottom of your Zoom screen, you will see a reactions button or over in the chat window. And what you will do in order to ask a question is raise your hand. And so if you will just click on the reactions and click the raise hand button, I will see that and we will enable your audio and you can ask your questions.
yeah, thank you everybody for staying. And surely you have something better to do on a Friday night, but thank you.
Okay, so we have a hand up from Antonio.
Apollo's really cute. Yeah, thank you.
That was wonderful. Thank you. How many years you've been doing this at Devon?
Every summer since 1997, except this past summer in 2020 when we didn't go because we can go anywhere. But yeah, every summer. So, we don't spend a whole summer up there. We lately we've been spending about 3 weeks or so each campaign. But yeah.
Do you think you'll consider some longer stays, or is there some point at where the weather means that you're locked in and you're going to have to stay until spring or something like that?
Oh, that's a good question. We are able logistically to do longer stays. It's just a cost, right? Because you have to get ready for the winter over, so have enough supplies and fuel and then backups for that. At any given time at our camp, we actually have enough supplies at this point for roughly 3-person years. So
Wow.
So a person could spend 3 years up there.
Wow.
Be okay, probably. But it's not how you don't want to be using those reserves by going in with a crew right this minute. You would want to bring in what you need for your mission and then have those reserves as a backup. But it's just a matter of cost, really, and funding. So far, what you have to also realize is Devon Island loses a lot of its attraction, which is the rocky terrain, very quickly. So you see bare rock usually from roughly June through August, and then even in May you still have a lot of snow cover on the ground, and then come September you often have quite a bit of snow on the ground too, and then there's a point at which planes can no longer come in on just tires because they're landing mostly on snow, so they have to switch to skis. And then you yourself on ATVs, you would have to switch to snowmobiles. And we don't have snowmobiles right now at camp. We had some in the past for winter operations, but we only have ATVs right now. So nevertheless, we could still do a winter over. And if it's a matter of just bringing in 3 or 4 snowmobiles, that's easy to do. Again, it comes down to cost. And the winter has a lot of interesting things we can do in the winter that we could not do in the summer. Radar, for example. I've been in touch with various radar teams over the years, and there's always been interest in doing some deeper geophysical sounding. Radar, the enemy of radar is liquid water. Liquid water acts like a mirror in the ground. So if you have wet soil, you can't see what's on the ground. But if you want to test the Mars radar, that's going to be very happy on Mars because the ground is so dry. So I mean, it has no liquid water. Devon Island would be a very good place to test that kind of radar system in the winter when all of the water in the ground is frozen. And so now it becomes transparent to radar, and we could probe deeper. So my point here is that there are things we can do in the winter, but we just haven't. And if you have a budget for us, on the other hand, I'm happy to chat with you anytime.
No.
All right, let's go to our next question. That's from Stephanie Baxter.
It's not, my name's Evan, by the way. It's just, this is my mom's.
Oh, okay.
Hi, Evan.
Like, what else do you specialize in? But I meant, like, what else have you worked on besides this Mars thing?
Well, I'm a planetary scientist, so I'm interested in not just Mars, but also the moon. Lately, in fact, with the help of Brian Day at NASA Ames and a few other scientists, we've been looking for caves on the moon. And caves on the moon have been known for quite a while now, for maybe a few years. But what we found recently were some caves, some candidate caves near the North Pole of the moon. And those are very interesting because unlike caves that are found elsewhere on the moon, which most of which are at low latitudes, so near the equator or not too far from the equator, the ones near the North Pole are never going to see sunlight because sunlight never enters these caves. These are basically pits in the ground. So think of a hole, like a golf hole, if you will, in the ground, except that of course it's much bigger than a golf hole. It's 15 to 30 meters across.
Yeah,
But
exactly.
these pits are essentially collapsed roofs of underground tunnels. And these tunnels were made by lava a long time ago, either volcanic lava or impact melt lava. When an impact takes place, it melts the rocks, so you can have some lava for a little while. Anyway, these tunnels were once filled with lava. The lava has now drained out of these tunnels, and sometimes these tunnels over time collapse, and all of a sudden you have an opening at the surface of the moon that gives you access to these tunnels. So anyway, we found what we think are some candidates for some of these tunnels and cave entrances near the North Pole of the moon. So we're talking about 500 kilometers only from the North Pole. And that's very intriguing because now these caves are going to be so cold that they might actually trap ice, water ice, over time. And therefore they could be a way of accessing some ice on the moon without having to go all the way to the poles, for example. So that's another thing I've been working on. I've also been working a little bit on the moons of Mars. Mars has two little moons that are really amazing. They're shaped like potatoes. The biggest one is about the length of Manhattan Island in New York. So they're very small worlds. And Deimos, so the bigger one, the one that's the size of Manhattan, is Phobos. The smaller one is Deimos. And both are very intriguing. And there's actually a Japanese mission that's about to go to Phobos and sample it. So that's going to happen in the next few years. But we're still very puzzled by what Phobos and Deimos might be, because although they look like asteroids, they might be leftovers from Mars's formation, in which case they would not be asteroids. Or they could be even captured comets from a long, long time ago that have broken up at times and reassembled as well in Mars orbit, at least part of the comet material. Or they could be ejecta from Mars. Some people have proposed that there were large impacts on Mars and then debris was thrown into orbit around Mars, and then these debris reassembled into these little moonlets. So we have no idea what these moons are. They were discovered by an American astronomer, Asaph Hall, in 1877, and we still don't know what they are. So to me, they are places we'd like to go, even with humans, to go check them out.
Yeah, makes sense. Thanks.
Yep, thank you. Good question, Evan.
Our next question is from Hallie Fairbanks.
Yeah.
If you are there, there
Hi.
we go.
Hello, hello.
I actually have two questions. So, number one, what is something that you do in Devon Island for fun, and what is something that you do in Devon Island for fun that you can't do on Earth?
Oh, they can do it. Okay. So we try to spend most of our time on Devon Island working and doing field work, but a lot of the field work is fun. So for example, last year we tested some kites that and this was a research project actually. There's enough wind on Devon Island to fly a large kite over your base camp almost all the time. And so it was like an observing tower to have a camera underneath this kite. And that was a very fun thing to do. Sometimes we've also attached some of our kites to ATVs. And so when we're driving around in the countryside, doing our field work, we are also capturing aerial imaging, like pictures from the sky of ourselves doing field work with a camera underneath a kite. We've done this in the past with balloons as well. That was also fun. So flying kites is actually a nice fun thing to do on Devon Island if you have especially a camera on the kite. Another thing we like to do is go, when we have a bit of free time, go look for fossils. And our research project doesn't really focus on fossils, but we're still interested in some kinds of fossils, like fossils of ancient algae, things that are very simple life forms. There are fossils of that on Devon Island, and we think there could be fossils of that on Mars. So we want to understand better what these fossils would look like if we were to find them on Mars. So we go fossil hunting. That's another thing we like to do on Devon. A lot more things. I like to fly my drone when I have time, not just for work, but as in for fun. And I go for hikes with my dog. Somebody said my dog was cute. Thank you. His name is Apollo. Yeah, he is cute.
Okay, David Anglin, let me ask you to unmute. David, if you're with us, there we go.
Yeah, thanks a lot. I've read recently that there is migration, quite a bit of magnetic, the magnetic poles on the Earth. Is there something similar to that on Mars? And does polar magnetic migration affect your instrumentation or any type of your work that is applied to Mars?
Yeah, interesting. Yeah, so that's a good question. On Mars, there is today no magnetic field to speak of. What we have on Mars is what we have in some regions, a relatively strong remnant magnetization. So it's a frozen, if you will, field from the past. But there's no significant magnetic field around Mars today. Now that tells you that there's probably not a lot of liquid metal churning in the center of Mars anymore. It's probably become very sluggish and cool down quite a bit. That's the general interpretation of why we don't have a magnetic field for Mars. And however, in the past, we know that there was a magnetic field on Mars. And in fact, not only that, but like you point out, it was migrating and there were probably polar flips. So the North Pole would become the South Pole, the South Pole would become the North Pole, and the magnetic field would flip. Because what we see on Mars in near Hellas Basin in particular is a region where we see some beginnings of magnetic banding, like you see on either side of the mid-Atlantic ridge on Earth, okay, where you see different bands of volcanic rocks of different ages. Each rock of a different age has a different orientation of the magnetic field that is essentially a frozen picture of the magnetic field at the time. So sometimes it's pointing north this way, sometimes it's pointing north the other way. So we see this pattern of flipping in some very ancient rocks on Mars in the southern region of Mars. But that's an ancient field and it's no longer active and that's no longer happening. Now on Devon Island, we are very near the North Magnetic Pole. It was even closer to Devon Island in the past. It's moving away a little bit from Devon Island now. It's farther north. But we're still close enough that the magnetic field is still mostly vertical at Devon Island. It's telling you that you are at the North Pole. If you cannot use a regular pocket compass anymore on Devon Island, because you're essentially too close to the North Magnetic Pole. And unless you have a sort of a special kind of compass that has a free floating needle. But that actually causes problems with flying drones, for example, because for a drone, for example, to fly itself and maintain position and hover, for example, it needs to not only have a good GPS signal to have satellites telling the drone where it is, but it needs magnetic compass to maintain position, to know which way to fly to get back to that position. And that magnetic compass is unhappy when it's on Devon Island. So you cannot fly drones in GPS mode on Devon Island. You have to switch your drone to what's known as the attitude mode, where it's all manual and where you essentially ignore the GPS and the magnetic north.
Thank you very much.
Yep. Okay, that brings us to Jacob. Are you with us, Jacob?
So Yes, I am. So, besides the Arctic and Antarctic, where other places on Earth have you been?
Oh, thank you. Well, I've been to Iceland. I've been to, in particular, into a lava tube, like a cave, like I was talking about on the moon, but this one was in Iceland, inside a volcano, basically. Of course, the volcano is dead, and at least it's sleeping, and the lava tube was not glowing with lava. In fact, the lava tube had ice in it because it was so cold. And it was really nice to explore that cave because it gave you a sense of what you might find in some of these North Polar lava tubes I was talking about a moment ago. And you realize that not only do some of these caves have ice in them, but the ice is behaving like little glaciers. It moves over time, it oozes. And so you have inside these caves things like mini moraines, mini piles of rocks that were basically pushed by the ice moving inside the cave. It's really neat. So anyway, I've worked on caves in Iceland. I've also worked on impact craters around the world. I sometimes work in California, in Southern California, which is in our backyard. We go to Dumont Dunes, for example, which is a big dune field to test Mars spacesuits and how they would work on dunes, on sand dunes, hiking up and down sand dunes. We go to Hawaii sometimes to test rovers with NASA Ames. Terry Fong's group at NASA Ames has done a lot of field testing in different places with their K-10 rover and later generation rovers as well. So we've gone to really interesting places with these rovers over time, including Hawaii. So if you are a planetary scientist, you're sort of lucky. I consider myself to be lucky. You get to see a lot of places and weird stuff.
All right, our last question is from Andy.
Hello,
Yes,
Andy.
hello. Can you hear me?
Yeah.
Yeah,
Yes.
hi, thank you. Great talk, thank you. Just a quick question. I understand the history of using rechargeable batteries for power on these vehicles because they're convenient, they're well known, and they don't pollute. But have they tried alternatives like hydrogen fuel cells and things like that?
That has come up. The vehicles we use are either gas powered or electrically powered. We haven't used hydrogen fuel cells, but that is certainly one, high energy density solution that is being considered for things like pressurized rovers and even ATVs. It's still an open question because hydrogen fuel cells have a bunch of issues associated with them as well in terms of their long-term efficiency, their maintenance. It's and of course for bigger things you want to go nuclear. That's pretty sure. So as much as we've been very disciplined as sort of a human species so far in limiting nuclear proliferation into space, there's no question that we're not going to do great things in space without nuclear. So nuclear power is can be clean, can be done properly, can be done safely, but of course it requires discipline and obviously a peaceful mindset. But that's really the way to do powering on the moon, especially to survive the lunar night, and on Mars as well, and going to Mars and coming back. So nuclear power, I anticipate will finally come of age when we realize that there's no real alternative to it.
Yeah, it makes sense. Thank you.
Yep.
All right, Dr. Lee, I think that's all we have for questions. I don't see any more raised hands.
This is Brian. I don't have the option of raising my hand, so if you don't mind, I'll just jump in real quick. Pascal, I really appreciate the discussion you presented about the sacrifices you make in the names of planetary protection there on Devon Island. Planetary protection is something that at NASA and at SETI is taken very seriously. It seems, though, that there are certain societies and perhaps entrepreneurs who are interested in colonizing Mars who have not given planetary protection as much thought. Can you think of ways that analog studies such as those that you conduct can help us better understand the importance of planetary protection and how we can go about doing planetary protection?
Yeah. Yeah. I mean, when it comes to science, planetary protection, so the idea of planetary protection, of course, is to make sure you don't disrupt or disturb the environment that you are studying and exploring. I mean, that's one aspect of it. So that part is a little bit like, the Heisenberg principle in physics. You cannot go to Mars and explore Mars without disturbing Mars a little bit. But what you want to do is minimize your impact, be a good steward, not just go there and treat the place like it's an open dump, and from day one have good practices in terms of your management of waste, your dumping of waste in the first place, etc. So on Devon Island, it has become second nature, even though we have some pretty stringent rules about not doing this, not doing that to protect the environment. You start living with these rules and they become just your way of life, and you're not even worried about it anymore. So I think that there's largely an issue of wanting up front to be a good steward of the place you're going to explore, and then deciding on the procedures and guidelines you want to follow for good stewardship, and then just going with them. Now, of course, there's more, there are bigger imperatives as well. I mean, you're looking for life on Mars. You really don't want to be inserting your own life because you want to find life that is from Mars or of Mars. So I think that's going to require some interesting approaches to sampling, to analyzing the rocks and the places that you will suspect might have life on Mars. We've been finding that using drones, for example, is a really interesting approach, because you can really control a drone very precisely and get it to collect samples in a sort of a surgical way almost, and bring back your sample in a way that you don't get to touch it, to a place that you can keep clean, and and then analyze your sample from then on. So there are ways of exploring by using robots like drones that humans could use to explore Mars very efficiently and at the same time very cleanly. And of course, there's also the issue of planetary protection in the other direction, where you want to protect the crew from whatever might be living on Mars. If it's living on Mars and you're there, might you be infected? And then if the crew comes back to Earth, might they contaminate the Earth and everybody else on Earth? And I think, before COVID, we might have thought that this was far-fetched as an idea, but I'm sure that most people would realize that, if there's anything that we know is alive coming back from Mars, we would want to protect ourselves from it before we just get sloppy and bring it in without procedures. So I actually suspect that, everybody wants to be on the first crew going to Mars, but I think that the very first crew to Mars will have a huge responsibility, especially when they come back. If we do find life on Mars, especially living life, and the crew is coming back from Mars, the practical solution to making sure that they don't back contaminate everybody else on Earth is quarantining. And we've done this for COVID. We do this for all kinds of infectious diseases, and that's how you would have to handle a crew coming back from Mars, just like we did the first Apollo crews from coming back from the moon. That was done mostly to appease, the general population on Earth, because we were really not expecting to find anything living on the moon, nor that we have any evidence of it to begin with. But if we are going to Mars to look for life, and so we can't say that that's not something that could happen, that we could find life on Mars. So I think that the crew coming back from Mars will have to agree to subject itself to a very long quarantine, and not even on Earth. I suspect that it could be on station or the gateway, or even on the moon, in some sort of a facility. That's the price to pay to be the first on Mars, is that you're not done when you're back on Earth, so to speak, or near Earth. You still have a long quarantine to go through. And I suspect that that quarantine could be of order a year or two. Again, just because some infectious diseases have that kind of gestation time. So or at least infection time. So that's actually an open debate. Some people think that we can just come and go as we want with Mars. I would say the very first people who go should be prepared for long quarantines, as opposed to not going at all, which is what some other people say. You shouldn't be going at all to Mars because of this alien life issue. Anyway, it's a longer discussion.
Okay. Well, on behalf of the PAS and everybody here, thank you very much for your amazingly excellent talk. That was really fascinating to me. I'd
Thank
like
you.
to thank everybody else for attending. And our next meeting is May 14th. We don't have a speaker yet, but that's the tentative schedule. We will, of course, announce it in our usual Google group. So unless there's anything else, I think we'll call it a night.
Thank you. And if you have further questions, feel free to email me at plee@seti.org, PLEE@seti.org. Thank you.